In this example, I will describe the somewhat more intricate interpreter design pattern. The interpreter design pattern makes use of other patterns. It's not very commonly used or implemented, but it's powerful and it makes use of other patterns as part of its definition. So the context in which the interpreter can be used is this. Suppose we have some external language, domain-specific language. In this case, it's a miniature Lisp language. Those of you not familiar with Lisp, here are some hints. Lisp is built on simple syntactic elements. Every expression is delimited by left parenthesis, right parenthesis. And all expressions are written in prefix form, meaning that the significant keyword or operator is listed immediately after the opening parenthesis. So this is a definition of a function. It's called fac for calculating the faculty of x. Preceding its name comes a list of parameters. In this case it's 1. And this is a comparison between x and 0. So in prefix form we write the operator first and the operands afterwards. Also the keyword, if, then condition, consequent, and antecedent. So this is a definition of factorial function, and this is an application of that factorial function on 5, which should result in 120. To test this, we have two methods for testing that we can evaluate the definition and that we can apply the definition on a value. In our interpreter, there's a top-level functionality for reading an expression and transforming it into some kind of an object graph. And everything that is not a constant, such as a number or symbol, is a compound expression. And when we read the definition of this faculty function, we expect it to be a compound expression. So our test is that we read the external representation of our function and we evaluate it in that which we call a context. So if we imagine that we proceed with invoking the faculty function on 5, we need access to the faculty function, obviously. But also, in our top-level context, we want to look up built-in functions, such as multiply and subtract, which ought to be defined in that top-level context. And as a test, we assert that the definition that we've read and created is a compound expression. Now, if we just look at what this interpreter pattern means, then we'll have to start with the top-level objects that we class we're likely to find when we evaluate expressions with an interpreter. The interpreter makes use of some kind of structure where, in this case, we have an interface expr, where each type of expr is responsible for evaluating its own value in a given context. So a number evaluates to itself, and when creating a number, we supply an integer value, which we can obtain later. A symbol, likewise, a symbol is used to obtain references. So a variable is a symbol, and we use it by looking up the value in the given context. Hence, our use of the context. Binary expressions such as multiplication is evaluated by creating a new number, the value of which is the value of the operands multiplied together. And the sub means that we create a new num type expression with values subtracted from one another. So here we implement in each type of expression functionality for calculating results, evaluating each expression's value, resolving symbols, returning numbers, and performing calculations. Obviously, we also have other kinds of expressions, such as function calls. Function calls might be the most intricate expressions to evaluate, where we have to evaluate all the concrete arguments. So for all the arguments, we evaluate them in the current context. We create a new context for invoking the function call, so we don't destructively change the top-level context by invoking it. And then using the definitions body, that is, that which is the definition of our faculty function. We evaluate that body in the new context that we create by mapping parameters to concrete arguments. This is the definition of how to evaluate a function. A conditional typically consists of a condition, a consequent, and an antecedent. So if the condition evaluates to true, then we evaluate the consequent, otherwise the antecedent. So all these expression classes contain implementations of evaluate, and evaluate return something of type expr, and the implementations differ depending on the specific type of expression. So, let's try to run all the tests associated here. Would you use JUnit and run both tests for reading variables and function definitions, as well as evaluating the different pieces of functionality. So the tests that have passed, all of them, asserts that when we read this string, which is the function definition, we get a compound expression as the result. And when we apply faculty function on 5 in the top level context, the resulting value should be 120. So the only thing that we haven't really dived into is how does this translate into some expression which can later be parsed and analyzed. Well, that's where the read method, the method which in the interpreter design pattern transforms an external representation into an internal one, and using that internal one evaluates our expression to whatever our language dictates. In some cases, the interpreter design pattern includes a notion of this read type functionality. In other descriptions, this is excluded because this is likely to be application specific. Clearly, the implementation here and the fact that we read a string is specific to our choice of language. So our choice of the Lisp-like notation we've selected here makes it possible for us to read using very simple string manipulation, a string, and create an expression type object. But given another type of language, we might not be able to do the same thing, and we might not even consider the read functionality to be part of the interpreted pattern. So, reading is rather simple. The only thing that we have to do is to ensure that when we encounter an opening parenthesis, we create a compound expression, and we add to it all the elements that that are part of the expression before we arrive at the end right parenthesis. If we parse an integer, then we create a num-type object. Otherwise, it's not an integer, it's not an opening parenthesis, we assume it's a symbol. That's basically it. And apart from this parser, every piece of functionality in our interpreter is delegated to our specific node types. So conditionals are evaluated by implementing a specific class for that type of node in our tree, and providing an implementation of the evaluate method given the current context. So the context is particularly useful when we do function calls, in which case we create a new context for the function call to simulate a stack frame, and to look up top-level context definitions. So the context class contains some static top-level bindings between symbols and abstract notions in our language here.